So, okay, welcome everybody to this second edition of the Julia course. It's a really pleasure for us to have you here because for the first edition of this event was only online on YouTube, so it's the first time we have students present. And this short presentation about to introduce AI2S and our next event, and to explain briefly, introduce briefly this course. So, AI2S is a non-profit association that has the mission to build a community of students interested in AI. And our objectives are to organize thematic events in the field of AI and data science for both for students, but also for researchers, professionals, and citizens. And we are currently organizing social events for promotion of the knowledge of AI. So, sorry, Marco? Sorry. Okay. Great. Perfect. Okay. With these events, we try to connect students with local and international companies and research entities. For example, here there are the logos of research entities. And briefly, we want to give more opportunities to the students that are interested in AI. So, what about this Julia course? Today, there is the first lesson that is an introduction to this Julia programming language. And Friday, there will be the second part of this event in which the professor will introduce the main libraries for machine learning, data science, and data tools. But what about the lecturer? The lecturer is Luca Manzoni, associate professor Department of Mathematics and Geosciences at the University of Trieste, and his topics of research are mainly about evolutionary optimization, and he at the moment is teaching computer science, global and multi-objective optimization, and information retrieval. So for more contacts, you have the mail. If you are interested, you can contact him privately. Here is QR code. There is the course material for the first lecture. You can scan directly, or you can go to our YouTube channel, and there is a direct link to download the required material of this that will be explained in this lesson. Notes, slide stream, the comments from the home, comments and questions can be asked from home on the chat, and moderator will select the question. And if you have a question here, you can ask, and I will give you the microphone here because we have a limited ability. So recording will remain available on this on our YouTube channel. So if you are interested in recovering some concepts, you can go online. And the last one, so I invite you, if you are not already in our association, I strongly invite you to join us because we are a non-profit association and we need new people that show and share with us their ideas. So if you have ideas, want to organize some projects, join us because we really want you. Yeah. So these are our links for interested people. And that's it. That's all for this presentation. So I think that we can wait for our lecturer, and then we can start with this event. Thank you.
unfortunately was in a meeting that was a little bit late, and then I found no taxis available, so I had to find a way to land here. But thank you for waiting, and let's start it. I am Luca Manzoni. I am a professor of computer science here at the university, and I'm also a user of the Julia programming language, of which there will be two lectures. The first one today will be more introduction to the language, and the next one on Friday we will see some of the application of machine learning based computing of Julia. So why another programming language? We have a lot of programming languages since the 1950s, Python, Lisp, and COBOL, and so on. We are the new programming languages as a way to express procedures, algorithms, and way to perform computation in expressing them in different ways. So, but we already have a lot of good programming languages of different level of abstraction, and particularly we have generally two kinds of languages that are of common use in machine learning, data science, and scientific computing and high-performance computing community, which are some high-performance languages. Is they compile down to method like C, C++, or Python, right, the oldest one surviving language. So yeah, they can be difficult to write compared to other languages, but they're fast. It is not trivial, but it's not impossible to get good performances out of Python and C, C++. However, what we actually use for data sets is a new language. We use languages that are a lot easier to write. Python, depending on your general background, if you go for computer science, statistics point of view, or MATLAB, that are easy to write. They tend not to be so fast. However, they are, even if there are a lot of ways to try to make them fast, so we end up with what's called a two-language problem. So we have a lot of high-performance libraries written in C or C++ or Python that are glued together using Python or any other higher level programming language. So we end up with, for example, NumPy, which is actually compiled code, which can be very fast, but which is exposed as a Python library. So you can actually use exactly that library and write fast code. But in general, if you want to be fast with something that is not implemented in one of the libraries, you need to go to a different language. So more or less, we need to know two programming languages. One for common use and one where we need to have high performances. So here, the inventors of Julia in 2001 wrote this article saying actually what they wanted from Julia as a programming language. So a language that which is as fast as C, which is as dynamic as Ruby, which is another high-level programming language. It's not only fast but also extremely flexible, and in some sense with characteristics from many other programming languages. Lisp markers, which what are its characteristics? Well, first of all, the point is type inference, so you don't have to explicitly state the types, but you can if you need, and you can actually specialize the function according to the type. So with his just-in-time compiled means that while you don't have executable, if you can, without using other packages, you don't have executable, executing directly as a script as Python, but the code is there. While just-in-time optimizing can be extremely fast. Support for metaprogramming. What's metaprogramming? Well, the idea that you can write code that writes code. So you can use Julia code to generate other Julia code. This is something that well, it's now getting a little bit of traction. It was actually the DNA of Lisp from the beginning. The idea that your code can be used to write code at 100%. Still, with the model syntax, so that using it is not like using something familiar, like Python. And with a lot of interoperability resistant code. This is not the topic of today, but we'll see that expecting that we can actually call Python and PyCode quite easily. So you don't have to have write an entire code base from one language to another. You can start the grammar. So, what to expect for this course? In general, we will see an introduction to the language, some of the packages next to actually the 2 hours in final. But we will not go in depth into any specific package on Friday, but because it would simply require one lecture for each package at least. And you can consider it as an introduction by a Julia user that is satisfied by the language to other people that may be interested in it. So, let's go to the code. So, if we look to the code here, we will start with by seeing that as with Python, you don't have any other high-level languages. You don't have to declare the type of variables or the type of the variables. Here you simply have as a type. So each variable in this case can be bind to a value, and the value has a type. And this is actually one important part. This is true also for most programming languages, but well, as you can expect, you can assign also other types. The type of the value will change, not the variable. There is no type of value. The type is of the value. The variable is bound to, and you have a lot of many different types which can be useful. Like you can have fractions. In this case, the type the function is not. As you can see, the type here is rational, while of instance for values. So you can actually have work with rationals and have all the computation be exact, and only at the end go to a floating point number. Sample for complex numbers, but this is everything quite standard. And as you can expect, sum and for different types is overloaded. So you have different sums defined for different types. We will see how we can actually define the sum for different types by ourselves. So if we define like for example in C++ where you can define the different, what is the behavior of different operators. So what is the sum between the two strings. Here you can define actually the same. As with other languages like Python, we have exponentiation in the language, except that it is with caret instead of the double asterisk. And integer division, as you can see now, with a specific symbol. How can we type that symbol? As with LaTeX, if you know LaTeX, you can actually, since we are language, acknowledge the existence of characters outside the standard 7-bit characters. We can use the entirety of Unicode. Yeah. So not only we can have integer division represented as div here, but we can actually assign it to a variable like so this tends to be useful in the case you are actually implementing something from a paper. You can actually use the same notation as the paper and more or less have a one-to-one correspondence between your code and what's written in some textbook or in some paper. As usual, you have the reminder. Now it is more or less universal to use the percent sign for that. But this is all, everything's quite standard up to now. Some small changes, like the fact that you already have, let's say, native rational types, and the fact that you can use Unicode, but apart from that, it seems Python. So, but we will see going forward that the more we go forward, the bigger the differences. So characters, single UTF-8 character. So you can actually have so if you are accustomed, for example, to work with C, a character in Julia is not the same character in C, char in C. String, as you represent, is enclosed by double quotes. As up to now, we can still see that, well, still is everything like any other, a lot of other languages that we know. We still have to see the difference. So we can have multi-line strings and enclosing them by triple, double quotes, and also strings containing quotes themselves. First difference, strings can be combined with the asterisk, with the times operator, instead of the usual plus. This is actually a little bit more creative. Plus is usually employed where you have something commutative, which is clearly not the case for strings. Now this is a small part, and you can interpolate strings simply by putting a $, before the name of the variable to interpolate. This is a little bit better than the older style Python without the format strings, and this is more or less similar to the idea of using format strings. So you can interpolate variables inside a string. If you want to interpolate entire operations, well, just interpolate the string, interpolate in the string by simply putting the operation to perform in between parentheses. As with Python, we can define multiple kinds of strings. This is simply a notation similar to string, but the actual representation is different. The idea is that you can take, instead of considering the string as a sequence of Unicode characters, you can simply take the string as a series of binary values, so by propending it with B. So, in this case, a collection of bytes, so unsigned integer of 8 bits, or even regular expressions. So, in this case, by pointing it by R, this can be used as a regular expression. For all the libraries that Python, for example, mention according to the regular expression, or that you can use to extract data. And up to now, everything's still quite standard. Do you agree? Yeah? Okay, first define something that tends not to exist in many languages, which is the symbol. What is the symbol? Well, the symbol hello is hello. What? Well, in a lot of cases, when you write code, there are some situations in which it is what you want is not something containing well, a specific value, but simply the fact that you have multiple values, like what you have enumerable types in other languages. So you can say what are the possible colors: green, blue, red, and you simply need three different values. Well, here with types, what you can actually do is to say, I don't interested in a specific value. This is simply a symbol for hello. So what is the kind of, for example, what is the, do you want to perform a statistical test which is two-tailed or single-tailed? You can have the symbol represented by the colon two-tailed, colon single-tail, and this simply, you have either two symbols can be equal or different, or you cannot perform other comparison or not. So this is the idea to have something that will be used when you need multiple values, but the only things you are interested in the values is that they're either equal or different. And you may want to give a name to the values. Like in C, when you perform a define, for example, infinity 7, because you need simply a number representing infinity, you are simply assigning the fact that you have 7, you have another number. Generally, it's not important. You only need to know that you have a name for something. So, a symbol that can be created by symbol and then a string, or a type of, or by using the colon. So here you can also what is the value of hello? hello. The value is itself. And you can simply compare it to other things. Is this symbol equal to hello or not? So it's not useful when you have parameters that can assume an infinite number of values. So you can, more formally, symbols are entire strings, and you can use them every time you want some descriptive name, but you don't need an entire string. And that's the first thing. Symbols actually are very common in Lisp, in the Lisp language, but say something not that used outside of that. Okay. So first difference, and then we will move to other differences. So arrays can be defined like Python lists in enclosing them by square brackets. So this is a vector of integers. As you have a type associated to the value. We will always have a type associated to the value. And in fact, we can find what is the type of the value contained in 64 and get the length as vector. So everything quite standard. We can have mixed type value. In this case, notice that you have vector of any, why any? Well, because if you perform the union of integer, what is the existing more general type containing 1, 3.4, and you string hello, while is simply a generic, what you can call it, object, any. And this would be less efficient, because in general you can have different implementation according to the types of the vectors. So in some cases, like in this case, when you have mixed type, you will probably have a vector of pointers to the different values. While in this type you can have, in this case, you can have something that is more compact in memory. So while we don't need to define types, we will see that types play a lot of importance to the performance of Julia. In general, if you can have what's called type stability, that is, your variable is not changing types. Sorry, the value binded to the value is not changing types every time. Everything can be optimized a lot. So if the just-in-time compiler is able to determine that you are only using a variable for integers, well, you will have a performance with using directly integers, not writing. So you can be a lot more efficient. And now the most contentious part is a node to MATLAB. In Julia, arrays start with index 1. However, you can define offset arrays that start at any possible index, including 0. Like all normal people that start counting from 0. Or for minus 1. Or a good average. Let's start with the first index that is 0.5. So you receive a vector and you want to find the beginning and the end. In fact, when you write code, if you want it to work well also with vectors starting with any index, which is useful if you are working, for example, with a Fourier form or something, and you prefer the index not to start with 0 or with 1, but you want between in a different range, maybe. You can always get the begin, the first element by begin, and the last element by end. So, in this case, what you get is that in most cases you are able to write code which is actually ignoring what is the starting and index of the array. As usual, we can have subvectors, what is called slices. So we say that it is the starting and then ending index. Note in this case is inclusive, since we are not starting from 0 but for 1 in the usual case. The slice is inclusive. So first index is included, last index is included. Not the first, not half open intervals. And well, you can assign slice to variables. As usual, this will be a 2-element vector. However, and we can change the values. However, we have actually, in this case, we have actually copied. If you see, we have a W is the view, the slice from slice of size 2 of the vector V, but we have actually performed a copy. So if we modify W, we are not modifying V. This is something that we may not want to do. Like, for example, if we are implementing something simple like a quick sorter, we may want to simply give the entire either to give the start of an index or simply give a view of an array which is smaller but which is the same underlying memory. So passing a pointer instead of passing a copy. Can we do this? The answer is yes. View of the vector V between element 2 and 3. Notice that the type now is different. This is a view of a vector of integers. And between indexes 2 and 3, we type index 4. In this case, if we change the value of the view, we change the value of the underlying array. So, by default, you copy, but if you want to work with the same underlying memory, which tends to be important when you are not copying 2 elements, but when you are copying gigabytes of memory instead, to work with views of the array. Okay, questions up to now? Apart from the fact that, yes, I know the problem is that array starts with 1. Nothing is perfect. Okay. So, as usual, we may want to do some broadcasting. If you work with NumPy in particular, you are accustomed to the idea of broadcasting. So, if you assign a scalar value to an array, you expect the same scalar value to be replicated into the entire array. Does this work with Julia? Let's try, and the answer is no. So, no broadcasting. Let's see. Perhaps use broadcasting. Oh, so there is some broadcasting. Yes. And the broadcasting is by using the dot. The dot perpendicular to a multifunction and operators simply means, well, broadcast it. In this case, the broadcasting works. So we have assigned from the element from the 1 to 3 of the array the value 4. So broadcasting must be explicit. You don't have some implicit broadcasting, but it is simple to do because it's simply a dot when you want to perform a broadcast operation. Clearly, you can have multidimensional arrays. You can represent them by separate them by semicolon or new lines. In this case, you have a matrix of integers, as we expected, and we can get not the length but the number of dimensions of the matrix, which is how many dimensions is the matrix, by n dims, number of dimensions, and the size is returning a tuple for the size of each dimension. One thing to remember, if you remember the difference between representing values in a row major or column major order, that is, you are continuous by column or row. Julia in this case is different, unless by default, from C, but because I need to interpret a lot with Fortran and so on, which is more or less something, a language that is still used a lot in high-performance computing, together with C++, is the same as Fortran for the in-memory representation of arrays. Which simply means that, which is a thing that you need to remember only in case you need performances. Say, for working with a 3x4 matrix, you will see no difference. How can we index the matrix? Well, by using all the indexes, one by dimension, separated by a comma. One thing to notice is that if there is a difference between an array of arrays and two-dimensional arrays or n-dimensional arrays, and you can see the difference in the type. Here you have a vector of vectors of integers instead of a matrix of integers. This is a two-dimensional vector. Also, the memory representation will be different. Apart from the fact that you can have different length for the different vectors. So just remember this, that vector of vectors is not the same as matrices, even if you can combine without too much difficulty with one and the other. As before, we can slice two-dimensional of n-dimensional arrays across multiple dimensions, obtaining sub-matrices, or using simply the column to get all the indexes in one or in the other dimension. As before, what we can do is also to work with the same underlying memory. So not by finding a copy, but instead working directly with the same memory. In this case, you have a view of a matrix M, and you simply say what indexes are you want the view on, and then what you obtain is something that behaves like a matrix, can be used like a matrix, but will share the same underlying memory with the origin matrix. And in fact, if we change some of the values, and the change is reflected in the original matrix. You can change the shape of an array by using the shape function, either in the same number of dimensions or using multiple dimensions, which tends to be quite useful because maybe you are importing something in one dimension and you have to reshape maybe 3, 4, 5, 6 dimensions, depending on what you need. It's simply, everything is simply shaped away, and you have a lot of different functions like zeros, and so on, that you can use to actually create matrices or n-dimensional arrays of any size with the predefined content. So you can work quite easily with multi-dimensional arrays. As with Python, you can use what's called array comprehension, in Python is list comprehension. Simply say that you want to fill an array with I squared for A in between 1 and 10. The range between 1 and 10. So the vector of squares, or even for multiple dimensions, simply separated by comma, all the variables we want to iterate on. So I times j for equaling from 1 to 5, j from 1 to 10. As you can see, 5 rows, 10 columns. So still, you say, quite normal up to now. Maybe there is more change, quite a small change in the fact that we have symbols and that we can easily define views of arrays, which is useful when you have when you need to use the same memory without performing a lot of copying, and having them quickly available is useful. And then we can also represent dictionary. A dictionary is simply defined as a dict. So you have key, arrow, and values. And potentially you can also use symbols as they can values. You can mix everything together. So a dictionary between any type and any type. And you can index it similarly to array. So A, or it may be 2, or even a symbol, foo. There's also, in this way also you can see if you want to actually give a name to some of the values that pass in a dictionary, instead of using a string, you can also use a symbol. You can assign non-existing keys. This means that the key will be added to the dictionary, and you can extract all the keys and all the values, possibly iterating on them. Notice that for each of them you will have a specific type, key set, and so on, that usually behaves exactly like an array or a list of values. You can also have tuples, so fixed array containers. In this case, a tuple can contain multiple types and they cannot be modified. So tuples are by default immutable. And in fact, in multiple cases, we have immutability. Not only we will see that in other cases, the default is immutability. Why immutability? Well, because it tends to reduce the number of bugs, but if you actually have to copy instead of mutate every time. If you really need to, you can stick by for mutation. Tuple. What is the type of this tuple? Is actually a tuple, and you see that the type is different for each element. That's not a problem because the tuple is immutable, so it's not like we can change the value contained in the tuple. And we can index it like arrays, starting with 1. If you want to define a tuple of only one element, it is not the different. A tuple of one element is not one element. You cannot simply use the parentheses because, well, you also use parentheses to define priority in operation and so on. So it will be ambiguous, so it's parentheses and a comma. You can also create named tuples so that you can actually index them using the names. So in this case, the name of the first value would be A, B, and C. And you can access them with the dot. Name a tuple B will return, in this case, 2. You can have destructuring with tuple, that is, if you have a tuple of 3 elements and you assign it to 3 different values, what is the only reasonable thing to do here? Well, actually there are 2 reasonable things. One is throwing an error. The other one, which is what Julia does, is actually assign the first element to the first variable, second element to the second variable, third element to the third variable.
And in general, this can be useful because you can have a function returning a tuple and assigning it to multiple values. So you can see it tends to be in some ways quite similar to Python, in other ways a little bit different. The difference will grow with time. Functions. Well, first of all, questions up to now? Yes? Actually, wait a second. Oh, okay. You ask if there is some list like structure where you can append or remove. Yes, in general, we see you can have multiple structure. We can perform append or removal, and you can actually perform append or removal also with vectors where there are functions push and pop that you can use then, like, well, as a list, but like a stack in that case. But in general, you can find structures also in the standard library that can be used for in this way. Have to allocate. Yeah. Okay, so yeah, there is a lot of, in this case, a difference. Depending on the structure that you use, you will have the same difference. In this case, you can say the vectors are more similar to, you can consider them as a first approximation more similar to NumPy vectors as a first approximation. Well, actually, then if you actually need to use a lot of append and removal, maybe you want to use a different data structure or that can be more suitable to this. So, going forward, we can start defining functions. How is the function defined in Julia? Now, instead of def, as in Python, we have a function, name of the function, and end. Indentation is not required, so it's not used as a semantical, syntactic element like in Python. But you actually, if you actually want to make the code readable, you need to, well, as you know, you need to actually perform some kind of indentation. So this is the function that simply return the value, the input parameter, the value of the input parameter plus 1. But actually, we can simplify it because the return keyword is not necessary, because by default you return the last operation that you performed. So this is exactly the same. We simply say what is the function add 1, x plus 1. The default is to return the result of the last statement. Actually, if your function is very simple, you can actually define it in line. So this is the same as the function definition. What is add 1 of x, x plus 1. So multiple ways of defining functions. So up to this, everything seems quite normal. You can return multiple values. So for example, you want to return the addition and multiplication of the two inputs. Well, simply return them separated by comma. You will return a tuple of all the elements. So in this case, you will return a tuple containing 7 and 12, and you can use tuple destructoring to actually assign it to multiple variables. So you can return multiple values. As with a lot of modern programming languages, you can use keyword argument. A keyword argument added after a semicolon in the list of arguments and can be initialized by default. If you have a default value, they are not mandatory. If you don't have it, they are clearly mandatory because you don't have a default value. So in this case, add constant x. By default, the constant to add is 0. We simply return x plus this constant. Add constant of 3. We return clearly 3. And add constant 3, and we change the constant. Well, you can pass keyword arguments quite easily, even in this case. And now we will see a few other definitions of how to define function, and then we have a small break. So you can have any number of arguments and collect them in a list of arguments. In this case, you simply append the 3 dots to the name of the parameter, and what you will obtain is simply a list of all the parameters that you passed. So in this case, var arg of 1, 2, and 3. X will be the vector 1, 2, 3, the list of, and you simply can perform the sum of all in this case. So you can have multiple, an unknown at the beginning number of parameters. So now let's have a 5 minutes break. by still talking about functions. And in this case, we'll talk about anonymous functions. So what you can call a lambda in other languages. A lambda is simply defined by, well, a tuple of the arguments, an arrow, and then the statement to be evaluated. So this is the generic function, and we will see what means with one method. And you can, since functions are first first level variables, is you can assign functions, you can pass functions as arguments, and so on. So this is a function, you can assign this to this variable, call it, and the type would be not too clear. Well, it is a function. You can broadcast for any kind of function. So in general, if you do this, like you want to apply this function to all pairs of elements of the two arrays, you will get an error. You try to find a method matching. This is the exponentiation between a vector and an integer. So what you want to do is to actually broadcast the function. And to broadcast the function, you simply have to append a dot to the first parenthesis. You will get a vector with all the elements obtained by broadcasting the function. So even broadcasting for a function is quite simple, and since plus and all the other operators are still functions, you can simply broadcast you can simply broadcast by appending a plus. As usual, you can perform one. We can define function, vector, and so on. We also need to use the usual selection and iteration. So you can use the if, no then, colon, or anything. It's simply if, boolean, something evaluating to a boolean, and then what to execute. You can combine multiple conditions as usual. This is exactly as in C. And you can have an else. Notice always the end here. And you don't need, as before, to use column and not anything else after else or after the condition of the if. You also have else if in case you want to use a chain of if else. And while. So while is, well, as before, while condition, the body of the while, and end. As before, you can see you can use Unicode. So you can have less or equal, which actually makes things a little bit more readable. And in the case of for is still for variable in something that can be iterated over. Then the body of the for. Notice that instead of in, you can actually use in. So if you want to iterate maybe across all the elements of a vector, for element in vector, which appears quite similar to the usual mathematical notation. You can also perform some kind of functional programming, say the usual map, which is execute a function for all the elements of something that can be iterated over. Map, apply this function to all the elements of this vector. Reduce is apply the function, take a binary function, apply the actually is apply the function to the first two elements, the result to the third element, the result to the fourth, and so on. So that's what actually means that you want to perform. Yeah, as a comment, you have 4 plus 5 plus 6 plus and so on. So in this case, we simply reduce plus on something, simply perform the sum of all. And in many cases, you already have something defined for the common use, like sum, product, reduced by sum, reduced by product, reduced by minimum, always take the minimum between two elements, or maximum, always take the maximum between two elements. So, while we can easily define, but I already defined minimum, maximum, sum, and product. We can filter the element of a list, so or a vector in general, returning all the elements satisfying that condition. We simply pass a function that must be function returning Boolean. So, given a value x, return 2 only if x is greater. Or if x is greater or equal to 5. So in this case, we will only get the elements that are at least 5. And in general, you can perform a lot of operations one after the other with this functional approach. That is, take maybe a random vector. In this case, a vector of floating point values between 10 floating point values between 0 and 1, of which we subtract 0.5. Notice that we use the broadcasting here. And then we want to find all the ones that are bigger than or equal to 0, square them, and sum them. So what we want to do is the sum of the square of all the positive elements in the vector. You can do it like that. V1 is the result of filter, V2 is the result of map. So filter greater than 0, map by squaring, and sum of all the elements. But this is something quite common. What you want to do is take the output of a function and put it into as an input into the next. Actually, as the last input of the next. So, can we do it without a lot of intermediate variables that are used only once? The answer is yes. And this is so common, actually, that you have this operator, vertical bar and greater than, which simply means take the output and put it as an input of the next function. So, filter of the element that are greater than 0, square all the elements. Notice that we receive an input as a vector, so it's squared with broadcasting, and sum of all the elements. So this is in some sense more similar to using the pipe operator in a shell. Like in a Unix shell, you want to take the output of one command, use it as an input of the other. Well, that's the same, except we can use it in our language to actually represent a sequence of operations one after the other. And in general, what you do is, given xf, you apply the function f to x. So instead of writing something like h of g of f of x, where you have to understand what's happening, you have to read from the inside out. So first f, then g, then h. You can actually use this pipe operation. When you pipe x into f, the output into g, and the output into h, which is a lot clearer to understand, because you can simply read the order of which the operation is performed is actually the order in which you read them. Okay, so up to now we have found how to define function, you perform the usual iteration and so on. Use some functional approaches to programming by using mapping, adduction, filtering, and so on. But we haven't used the types at all. We know that each value is a type. We haven't used the types. So let's start using the types. So we have a lot of possible predefined types: float, rational, integer, numbers, reals. Types can have a hierarchy. So a real is more specific than a number, and maybe an integer of 64 bits is more specific than a generic number or a generic integer and so on. And you can actually, with a double column, specify which type you accept as argument of a function. So in this case, we say that this function accepts two arguments that are real or a subtype of real and nothing else. You cannot pass something that cannot be considered as real. So this works: 3.5, 4.0, 7.5. If we try to call it with strings, notice that the arrow is not in the fact plus is not defined for strings. The arrow is that there is no method matching f on reals for where the arguments are two strings. So in some sense we are selecting which function to call according to the type of the arguments. So what if we define multiple functions with different combination of arguments but all with the same name? Will it work? Well, let's see. As you can imagine, it will work, and this is actually why it is useful. As a general note, you can also annotate internal variables, any variable with the type. In this case, you will get an error if you don't have the correct type. Okay. Some types are parametric, in the sense that if you have seen the curly brackets, maybe in vector, what you define is a generic vector of something, and the something is another type. It can be a vector of vectors, a vector of anything, a vector of reals, or it's a rational of int64, an array of integer of dimension 1, and so on. So in some case, you can consider them something similar to templates in C++, where you have can define things with a generic type, and it is instantiated for more specific types. And you can actually define unary types by format like unar or float 64, integer 32 will be something representing both integers of 32 bits and float of 64 bits. I don't know why this could be useful, but you can define it. And in some cases, this is actually useful because you want to consider together a collection of multiple types. And that's one example in which you want to do this. Maybe you want to work with data. You have an array of data and you have some missing values. Some of those missing values can have a special value missing of type missing. That is, we don't know. So what is the type of the array? In this case, it's not only maybe integer, it's not only missing because we have both of them. It's a vector of the union of the two types. So in this case, we accept a vector that contains floats and missing values. And what we will do, we will filter the missing values and sum the remaining ones. So in this case, we have missing 3.5, a missing value, 5.8, a missing value, minus 3. We expect the result to be the sum of all the non-missing elements. So that's one possible use of the union type. If you know what is the MA in me, you can find in some Python libraries and in other. As you can, eBay is exactly missing there. So now we start to see that types in Julia can be a little bit more complex than in some other languages like Python. And when we have types, we may not want only to define union types in the sense that either one type or the other, but also product of types. It is tuples or structures with types. In this case, we can have structures like pairs that contains two attributes, first and second, with no type specified here. We can create an element of this type, structural pair, by simply calling it with the arguments, one for each attribute. And as you can see, the type of this is my pair. Now, nothing strange to now. We can, as with class objects, Python, we can access the attributes using the dot notation. First difference, can we assign something? No. Why? By default, structures are immutable. Once you assign a value, once you create them, you cannot modify them. That's a choice. The default can be mutable or immutable. They decided the default should be immutable because in case you have immutability, well, you tend to think more if you actually need mutability, because with mutability you can get more bugs. First of all, for example, if you are in an environment with concurrency, if you have everything that is immutable, then you cannot have the problem that you have two concurrent threads or processes modifying the same variable, because you cannot modify it. However, if you really need to have something mutable, you simply provide mutable when you define the structure. This is something, a different type. So you can define a mutable pair, and now you can actually modify the values. We can also have force the types inside a structure. In particular, we can have some templating, like in this case, we say that we have a struct for each possible type, T, in which the two attributes are all of the type T, all of type T. In this case, we can define the same pair. Notice that now the type is changed by one specific type, in this case the integer, 64-bit integer. So this is a different type than the next one, because in this case what you will get is a different type, because the argument, the type, and notice that even if it was not clear at the beginning, you are now forcing the two attributes to be of the same type, because you are saying here that for each type T, the first and the two attributes are of type T. If we wanted them to be different, we would have needed actually two arguments, one for the first, one for the second. And in fact, we can force, if we don't need all the power of templating, we can actually force the different arguments to be of the different attributes to be of a specific type. So now we see that we have a lot of things that we can do with types. Why? The question is, okay, we can specify the type and get an error if we got the incorrect type. Why? Well, the reason in this case is for multiple dispatch. What is the idea of multiple dispatch? Is that you can call different functions depending on the type of all the arguments. If you know object-oriented programming, you have that you have implicitly for each method of an object a dispatching that depends on the type of the object. The same method for two different objects can be defined. So you are changing which function to call depending on the type of the implicit first argument, which is the object. Or in the case of Python, is this in the type of self, the first argument of the method, when you define it. So you can have the same method, the method with the same name in different classes with completely different content. But in that case, you are dispatching only on the type of the first argument, the self, on the type of self, not on the type of everything else. The idea of multiple dispatch: look at the combination of all the types, find the most specific function that you can call with the types that you have, and call it. So, for example, we can have the same function defined for floats, a float and an int and a float, or two ints. The body of the function is different, the function name is the same. And we can also define another with no restriction on the types that will be called when none of the more specific one can be called. And notice that we are actually calling different functions. So why is this useful? Well, this is useful because now you can use the same code and specialize it according to the types. So you can have the same maybe solve operation for a linear system and different implementations of the same function, one where the matrix is diagonal, one when the matrix is sparse, one when the matrix is upright triangular, and so on. Your code will be, the code using the function will always be the same. You will always call the more specific function. And if you see, you can call methods of a function, and you see how many methods you have. So, all the combination of methods that you can have. And in fact, if you see, even plus has some more methods. Like here you have a plus for a collection of a union of different sizes integer, floats, specific for floats and big float, for dates, for notice plus for symmetric tridiagonal matrix, and as B is a symmetric tridiagonal matrices, so we can define the plus between matrices. And well, you have a lot of them, bit arrays. Well, just complex numbers and so on. Actually, hundreds of methods. Why? Why? Because now, since plus is a function like the others, you can write another implementation of plus with a combination of types not covered by the existing methods, and then have plus work with other types. So you want to define types between structures that you define, you can simply function plus, open parenthesis, x of types my structure, y of type my structure, and define what is plus in that case. And then plus will work. Yeah, you can enter more or less say the typical internet argument of is Julia object-oriented or not? Well, if you see object-oriented as Java style or Python style, where you have to define a class and inside the class all the methods of the class, and you call the method with the dot notation, no. It is object-oriented in a more general sense, the same, for example, for the common list object system, which is the idea that you have structures that can contain multiple types, you have a hierarchy of types, and you have dispatching according to the type. So you can define an object system. You will call the methods differently because you don't have a special notation for the first argument like in Python or Java, when the first argument is actually outside the method call, but this first argument dot name of the method and then the parentheses from the second to the last argument. In this case you don't have a specific notation, but you can still define the same class structure. Your method will be external to the objects. Well, that's not a problem. That's also how the other languages implemented object orientation before the uniform way in which we learn object orientation today. So, let's continue. So, in general, multiple dispatch can be, as I said, can be not useful. Now, a little bit on how you can develop using Julia. So, unfortunately, you don't have an IDE like PyCharm or IntelliJ, but you can use Visual Studio Code plus the Julia package, Emacs plus the packages specific for Julia, and in general, you have multiple editors that you can use. You can create what's something similar, but actually a little bit more powerful than virtual environments that you have in Python. You can actually use this PKG package, and you call activate to create a new environment. Either you can install packages into the environment, you can remove them, update them independently. You will get a manifest DOM and project DOMs which contains all the information to recreate the same exact environment. In this case, at least in this lecture, everything can be installed. Everything is part of the main library. Next lecture, we will see something outside of the standard library. Okay, I think we have time, a little bit of time for macros, which is something that comes from the Lisp heritage of Julia. What is a macro? Don't think as a macro as something like C macros when you have a define, or when you are actually performing text substitution. Here a macro is a list-like macro, which means you actually receive code which is implemented as Julia objects, Julia structures, and you can modify it and output new code. So you can think of it as passing the code directly to a function without evaluating it before passing into the function. So for example, you have things like time, at time, all markers for visibility, not to avoid confusing them with function, are prepended by the at. And in this case, what this does is will take the code and actually add before and after the code all the necessary additional code needed to time the function and get the results. You can use the marker which actually say which kind of function you are, which of the methods of the function you are calling. So in this case is x of in this specific method. And you can actually inspect all the code that is generated at the runtime in the different levels by using macros to look at the code actually from the what's called code forward, which is actually a simplified version of Julia with a lot more restriction that is then passed to the compiler, which uses an intermediate representation. Actually, before you get the types, you can see we have type annotation here because type inf said, okay, we are summing 3 and 5, so maybe the type is an integer. Intermediate representation by the compiler, and even native code. In this case, the actual assembly code, in this case for a ARM processor of that actual function. So you can actually inspect what you are the code you are generating, and in case you want to hunt for performances, you can actually look at the code and say, okay, the code that I'm generating is not optimal, maybe because I'm expected it to have to be all integers. Now if I have an integer and here I have a string, which is not expected, and you can actually modify the code and try to get all the performance that you need. Actually, you also have a macro working on other macros, which is macro expand. Macro expand simply say, just apply the macro, and instead of evaluate the resulting code, return the code generated by the macro. So you can see macro expand timed of 3 plus 5, you have that you have a new variable. The code is generated, you have a variable that counts the number of garbage collection steps times in nanoseconds. You actually execute the function, get new time in nanoseconds, get the difference in the number of garbage collections performed, and at the end you get allocation time, garbage collection time, and all the stats that we need. So we actually took the code of 3 plus 5 and we added all that code around it to actually time it and get information about it.
Sorry, Luca.
Yes.
Does it time correctly also when multiprocessing or GPU calculations are involved?
Okay. In particular, in the case of GPU multiprocessing, you have actually another implementation of time, which in the, for example, from the CUDA package, which is actually you can use in the more or less in the same way of CUDA dot at time, so on, and that will get all the information also about the allocations in the not only the allocation of the system memory, but the allocation of GPU memory, and so on. So you, in some sense, you can have different markers for you can have different markers for different use cases in particular time with additional statistics for GPU compilation.
Okay, so thanks.
Okay. And this is one thing that allow Julia to be flexible, because, for example, if you want to perform even very complex code transformation, well, simply pass the code to a macro. The complexity is in the macro, not in you writing the code, unless you're writing a macro. Then you know what is something that you had to do in any case. So, in general, if you want to get a part of the code and to, without evaluating it, means you want to get a structure representing the code, not the result of executing the code, you can quote it. Quote this code, and in this case, what you get, well, is the code. You have assigned the result, you have assigned the code. And if you see, we can, what is the type of the code? Well, it is an expression. We can use this symbolic expression representation, which simply means that we have a tuple when you want to call the function plus on 3 and 5. And you can manipulate it because, well, it's a structure that in your code you can change part of it, modify it, like see that it starts with call, the arguments are plus 2 and 5, and well, I don't like plus here very much. I would like to have times instead of plus. Well, let's change the value from plus to times, and now if we evaluate the code, I actually change the code. So you can get a piece of code and change all of it and turn a new piece of code. This is useful because more or less what you are doing, you're performing even complex code transformation at runtime. Making it extremely flexible. And we are at 7, so probably we will not have the time to talk about linear algebra now. We will continue to talk about linear algebra on Friday, and then about other different packages. The small thing I wanted to show you is simply just before going back, is that you can actually use the Unicode iteration to do some very interesting stuff. So, thank you all of you for attending, and see you on Friday. Bye.
Okay. First of all, before you go away, if you need certificate of attendance, please come here that we collect the data and then we will produce it and send it to you by email. And also, I'm here in case some of you want to subscribe to the association. Just a quick impromptu by Yuri now.
Okay, so if you have some questions about this lesson, you can feel free to ask. And I will come with the microphone, or you can come here, or I can simply repeat. So if you have questions, raise your hand. And if not, we are happy to wait for you for the second lesson of Friday. Okay.
How does inheritance work in Julia?
Okay, inheritance works in the sense that, well, By default, if you define a more specific type, and you can define a type that is more specific than another, by default, all the methods working for the more general type will work for the more specific one. You will not have inheritance in the sense of your variable. You can only define more specific type, but the complexity is generally not in defining which are the private, the attributes, but what are the methods, and the methods where you get all of them unless you specify more specific ones. So you can still have inheritance. It works a little bit different than than in other languages. Say it's implicit.
Sono domande?
Secondo me non funziona benissimo. La validation non ci sono.
Ok.
Vabbè, si può chiudere tutto.
Un po' chiudiamo, dai, chiudiamo. Bene, bene.
Thank you all.